I am Dr. Sahaya Sudherson, Associate Professor, Department of Mechanical Engineering, Rohini College of Engineering and Technology. Today, I am going to discuss about the helical gear design using Lewis and Buckingham equation, which comes under the subject Design of Transmission System, subject code ME8651. Before we deal inside the subject, we can see about the course outcome. After successful completion of the course, the student should be able to analyze the concept of design in the flexible drive elements like belt, chain, and rope drives. The student should be able to develop a method of various types of gears with parallel axis. The student should be able to develop a method for various types of gears with inclination with axis. The student should be able to explain the techniques used in industrial design multi-speed gearbox application. The student should be able to categorize the suitable design for cam, clutches, and brakes for automatic application. Helical gear design using Lewis and Buckingham equation. Introduction of gears. Gears are among the most important powerful transmission elements. A gear is a rotating machine element having cut teeth with mesh with another tooth part, usually having teeth of similar size and shape in order to transmit power. Any tooth member designed to transmit motion to another one or receive motion from it by means of successfully engaging tooth is called gear. The Lewis equation. Wilfred Lewis introduced an equation for estimating the bending stress in the gear teeth, in which the tooth form entered into the formulation. The equation, announced in 1892, still remains the basis for most gear design today. Classification of gears. Gears: parallel shafts, intersecting shafts, non-parallel, non-intersecting shafts. Again, parallel shafts classified into 4 types: spiral gear, helical gear, double helical gear, ribbon gear. Intersecting shaft again classified in 4 types of gears: straight bevel gear, spiral gear, zero gear, phase gears. Non-parallel gears again classified into 3 types: spiral, hypoid, worm gear. Helical gear terminology: axis of gear, transverse circular pitch, base pitch or nominal pitch, hole depth, form diameter, base circle diameter, outside diameter, pitch diameter, helix angle, addendum, dedendum, lead angle, normal circular pitch, face width, lead angle, helix angle, front face, circular pitch, nominal pitch line, nominal plane. These are some of the helical gear application in industry. Helical gears. Helical gears differ from spur gear in that they have teeth that are cut in the form of helix on their pitch cylinders instead of parallel to the axis of rotation. Helical gears may be used to connect either parallel or non-parallel shafts. The discussion in the chapter will be listed helical gears connecting parallel shaft. In this case, a right-hand helix will always mess with a left-hand helix. A helical gear with the left-hand helix is shown in following figure. The following parameters are the important parameters of the helical gears: psi helix angle, F transmitted force, Fe end thrust force, Pc circumferential circular pitch, Pnc nominal circular pitch, B phase width, P diameter pitch, Pnd nominal diameter pitch. In order to contact on the face of the tooth shall always contain at least one point on the pitch line. The minimum phase width of the tooth is B minimum equal to Pc divided by tan psi. The pressure angle pi n. The nominal plane is distinguished from the pressure angle by in the transverse plane as shown in figure number 19.2. The relationship between tan pi n equal to tan pi cos psi. The rupture or formative. Number of teeth NF on a helical gear is defined as the number of teeth could be generated on the surface of the cylinder having a radius equal to the radius or curvature at the point at the tip on the minor axis on the ellipse obtained by taking a section of the gear in the nominal plane. NF equal to capital N divided by cos cube psi. where n actual number of teeth, psi equal to calyx angle. Strength design for helical gears may be handled by employing design methods similar to those gear used for spur gears. Assume that load is distributed as for spur gear and looking at the to nominal to the helix. The nominal load F1 using the Levy's equation is F1 equal to S into B divided by cos pi into pi y divided by P and D. Substituting the tangential force F equal to F1 cos pi and P and D equal to PD divided by cos pi. F equal to SB y pi divided by P and D. F equal to SBY pi cos pi divided by pi d, where K B divided by PC limited to maximum of PD. Diametral pitch Y is the form factor based the victual or formative number of teeth. The allowable stress may be taken as approximately equal to the endurance limit of the material in released loading, corrected for stress concentration effect and multiplied by velocity factor S equal to S0 divided by 7 S0 into 78 divided by 78 plus root of V allowable stress, where S0 equal to about 1/3 of the ultimate strength of the material, V pitch line velocity. A more accurate evaluation of S0 could be made if data regarding endurance limit and fatigue stress concentration effect for the material are available. However, in view of other approximation, design based on the above expression should in general be adequate, since it must also be checked for dynamic load and wear load as explained. In design check for strength, the pitch diameter is either known as unknown. If the pitch di diameter is known, the following form of the Levy's equation may be used. PD square divided by y equal to S0 k by square cos psi divided by f into 78 divided by 78 plus root of v, where k equal to b by bc, f tangential force, v pitch line velocity. Then the above expression an allowable numerical value for the ratio p square pd square divided by y, which controls the strength. If the pitch diameter is unknown, the following form of the Levy's equation may be used. S equal to 2tpd cube divided by k y pi square capital N cos pi, where S equal to actual induced stress, capital T residing torque, N equal to actual number of teeth. This expression gives a numerical value of the actual induced stress in terms of the diametral pitch. The above procedures based on strength design should be considered only as a first approximation is arriving at the possible pitch, and faced with it must be checked for wear load and dynamic load. The limiting endurance beam strength load F0 is based on the Levy's equation without the velocity factor F0 equal to S0 by phi cos psi divided by PD, where the symbol are the same as above. The limiting endurance limit load F0 must be equal to greater than the dynamic load FD. The limiting wall load FW for helical gears may be determined the Buckingham equation for wear FW equal to dB B QK divided by cos square pi, where dB pitch diameter of pinion, Q equal to 2dg divided by dB plus dg, K equal to S square is into sin pi n into 1 pi E P plus 1 plus EG. ES surface endurance limit. The limiting wear load FW must be equal to or greater than the dynamic load FD. The dynamic load FD for helical gears is the sum of the transmitting load and the incremental load due to the dynamic effect. So FD equal to capital F plus 0.05 root of CB cos square pi plus F into cos pi cos psi divided by 0.05 V plus root of CB cos square psi plus capital F, where the symbols are the same as before. Values for C, which is the function of amount effective error in tooth profile, may be obtained from the spur gear. FW must be greater than or equal to FD, and F0 must be greater than or equal to FD. Note that the F0 and FW are allowable values which cannot be exceeded. These are the systematic procedure of helical gear design using Lewis and Buckingham equation. These data referred by the reference book Theory and Problems of Machine Decision by Allen, S. Hall and Alfred, and Design of Transmission System by T. J. Prabhu. Thank you.